our session 10, we will be dealing with inventory theory and modeling. We will look at deterministic inventory theory in this session. In the next session, we will treat the case when demand will be stochastic. So here we will be looking at the very basic model of inventory ordering, which is called the economic order quantity. We will extend the economic order quantity to regard also positive lead times for replenishment. And then we will have a look on the case when we do not order our new items for the inventory, but we assume that we can make them ourselves so that we have a production rate at hand. And then we will look at a case where when we replenish, we can encounter quantity discounts. So the content of the lecture is inventory theory and modeling, and the special extensions to the basic model. The learning objective is how to develop such models for production and reordering, and how to develop an inventory plan. Here we are with respect to a time horizon. If we look at hierarchical planning for an organization, we will be looking at the midterm planning. If you record the master production schedule that is at the tactical hierarchical planning level of an organization, then this is where we find ourselves in. Here we will also regard then how to incorporate shortages, positive lead times, and as said, discounts. We will be looking at mathematical models that have a continuous time horizon. So we are not splitting the time axis into what we call buckets, where we can count for a time entity like a day or a week or a month, etc. But we will come to this at a certain point. So here, with respect to mathematics, what we will be dealing with is continuous functions, the derivations of the functions in order to determine optimal points of a function. You have a learning checker available to check if the knowledge that you acquired while reading our textbook, which is Hillier and Lieberman. So let's go to the very basic model for ordering. It is called the economic order quantity, which is the simplest and most fundamental model that we have in reordering, or also called inventory theory for planning models. It is quite extensively used in practice because it has quite some nice properties, and is also incorporated in software like for ERP systems and SAP and other commercial software. The basic assumptions of this model are as follows. We assume that we have a demand rate that is quite known, so we know which demand we will be facing in the next time period that we want to plan. So we have that number in units per time. We assume that no shortages are possible. That means that we have to fulfill the demand, which is known, and we do not allow for shortages to happen. So we would not have a back ordering log system where we note how much demand we will have in the future, and then we could go to a negative inventory and fulfill this demand at a later stage, but this is not allowed. So we will also in the first step, and this model also does that, assume that we have a zero order lead time. That means that as soon as we reorder, we have our order in our inventory. That is, of course, quite unrealistic, but and we will also see how we extend the model to incorporate positive lead times. But for the very basic model, this is what we assume to make and keep things simple. So the costs that we take into account for this very simple model are a fixed setup or ordering cost, depending if we look at internal production where we order for our inventory, or we order at an external supplier. This doesn't matter, but where we place an order. So every time that we place an order, we encounter a fixed administrative cost for that, either for setting up a machine or for the ordering of at an external supplier. We also encounter proportional ordering cost, denoted by C, per unit of ordered product. And we have an inventory holding cost factor H per unit that denotes the cost that takes us to hold an inventory item per one-time unit in inventory. We also assume that in the beginning we have zero inventory on hand, so the first thing that we need to do is to order inventory, and we also assume that when the time horizon is finished, that our final on-hand inventory is also zero. That helps easing things and keeping it, the first model, quite simple. So how do the cost functions and the inventory holding develop throughout our time horizon can be seen as follows. So let's have a look how we can be looking at this model from a graphical perspective. Let's depict the graphic. So here we depict our inventory. And here we have our time horizon that we denote by T. So the first we have, and this is 0 by the way, so the first thing that we do is we have to reorder, because we have the assumption that the initial inventory holding is 0. So we would order a quantity Q, and then in continuously our inventory will drop at a rate D, which is our demand. So we take out inventory one by one item as demand happens, and we wait until this drops to 0 for reordering. So this point is the order quantity divided by our demand D. When it hit 0, we will reorder again, and due to our assumption that the order will be immediately in our inventory, this happens all at once, and then we start a new cycle where inventory would drop to 0, which would be then a new cycle to QD. So let's look at the first cycle, the time that it takes to the inventory to drop to 0, we denote by T, and this is the quantity of our, or the amount of ordered items. So the first ordering cost now that we can denote is the purchasing cost. With our denotation that we have in the lecture slides, we denote this by a little c multiplied by D, our demand. And then we can denote the number of orders that we plan as D divided by Q. Now, so the cost now of ordering is are also our setup costs, are then denoted by a large K multiplied by the number of orders that we will do in our time horizon. So this is the first things that we consider. Then we need to consider the costs of holding inventory. So we have an average inventory holding cost. And this is then given by the average amount of inventory in our system, which is our order quantity divided by 2. And this multiplied by the holding cost factor H gives then the average inventory holding costs. So now we have all the cost components in place that we want to consider for our total costs. And here we have to denote that we want to balance these cost factors. So the cost of reordering, the setup cost that we encounter versus the inventory holding. So you can imagine if the setup costs, so the reordering costs are quite high, this in regard or compared to the average inventory holding cost, then we want to hold more, or we want to order more items because then we balance the cost. Vice versa, if we have a high inventory holding cost factor, if that is very expensive, then we want to order less items so that we order more frequently, because holding inventory is more expensive. So the total cost now that we regard, denoted by zeta of Q, is now composed by, get some space. They are now composed by the fixed ordering cost, or by the setup costs, plus the purchasing costs, plus the costs for inventory holding. If we draw these functions, or the different cost functions, we get this picture where we have here the total costs on our y-axis and the order quantity on our x-axis. So the inventory holding costs. So the average inventory holding is the following linear function. And then we have the setup costs, which are a function of Q as well in the denotator. So it looks like this. And now where these two functions meet or cross, we have the balance of these two cost factors, and that will be our optimal order quantity, the function of zeta. Then is the combination of them both. So this goes along like this. Who would like to see how we derive now this function, or this point of the optimal order quantity, I will show you how that works. So what we need to do is we need to take our cost function and derive it 2 times. So the first derivation of zeta q and we're deriving it for one bracket too much, for our order quantity. So here we look at the cost function and we see that we have the order quantity in the denotator. So if we take the derivation, this becomes minus k multiplied d divided by q exponential or quadrat. And we also see now that in the cost function, the purchasing costs are not dependent on the order quantity, so that drops out. And then deriving for Q in the inventory holding gives us H divided 2. And to find the optimal point, by the way, we also have to, this is the first derivative, we have to check the second derivative. If that is positive, then we have a minimum point, so we need to check that as well. I skip this for the time being. And then we set this to 0. I first put this term on the other side. So I have H divided 2 on the left-hand side and K multiplied by D divided by Q squared or quadrat on the other side. Now what we can do is that we take the inverse, because we want to find out the optimal order quantity. So we want to isolate for the Q. Then we take K multiplied D on the other side, on the left-hand side. And to get rid of the exponent, we take the square root. And we get the optimal order quantity given by the square root. So this gives us now the answer to how much to order. And the next is we want to know when to reorder. So we want to find out the reorder time, or the reorder point. And this we denote by our T, and we want to find the optimal T. And the optimal T depends on the optimal order quantity divided by our demand. And if we look at the graphic, we can see that this would be this point. So how much time can we last with the order quantity that we have just calculated? And in order to derive the term, I make it quickly for those who barely recall derivation in mathematics. So we take our term and set it into the optimal Q. Divided by H. And this is divided by D. Now we see how we can make this a little bit more easy. We have 2 times D. So we can, by using some algebra, we can make this look nicer. So, so I just use some algebra to rearrange the terms. So the D, this would be 1 divided by D, and this would be then multiplying by D minus 1. We can use the square root of each term or each parameter that we have alone. I want to care just for the D, so I leave the other 2 in the square root, and I just rearrange D. So this is actually the same as saying that is the square root, and then we have our D minus 1, and now we see that this would be D minus 1/2. And this we can rewrite then. I put this back in the square root, so our D would be 1 minus D n squared, and we can put this together in one single square root. So this would be 2k divided by h multiplied by d. And this is our optimal reorder point. So let's take an example now and calculate the optimal order quantity and the reorder point for the bookstore that orders pencils. So here we have the exercise. We have a campus bookstore that sells pencils of number 2 at a fairly steady state, 60 units per week. The pencil cost of the bookstore is for the bookstore is 2 cents for each pencil, and they sell it at 15 units each. The costs of the bookstore for initiating the order is $12. The holding costs are based then on the annual interest rate, and this is exactly what I said first. The interest charge multiplied by the purchasing cost then give us the inventory holding cost. And then we have to determine the optimal number of pencils for the bookstore that he should purchase in the time between the placement of the order. So here we are considering here a yearly inventory holding and reordering. So how much should that be? For this purpose, we regard 52 weeks per year. And now we need to calculate the optimal order cost, the optimal reorder point, and the total annual costs. So first thing that we need to do is we convert the demand to a yearly rate. So we have D is given by the 60 units, the demand, the weekly demand multiplied by the 52 weeks, and this is 3,120 units of pencils. Then we want to derive the holding cost factor H, and that is now, as said previously, the large E multiplied by the variable costs, and this is 0.25 multiplied by 2 cents, and this is 0.005 cents or dollars. Then we have the fixed ordering cost K given with $12. I think that's basically it. So the EOQ now, the total costs are given, I denoted as before. So we have zeta from Q that is given by the purchasing costs plus the fixed ordering cost or setup costs plus the inventory holding cost. I just write that down once again so that we have it in front of us. That's the total annual cost for inventory holding. And now very easily we can we have derived the optimal order quantity, so we just take our formula and plug in our parameters. So 2 times $12 multiplied by our yearly demand, and this divided by our inventory holding cost factor, and then taken the square root and this is 3,870 units per year. Now the optimal reorder point, big T, is the optimal order quantity divided by the demand, and this is 3,870 divided by 3,120, and this is then 1.424 years. We were required to state the total costs. So if we look at the average holding cost, that were the 0.005 multiplied by 3,870 divided by 2. This is, now I state the unit, $9.675. And if we compare now the average setup cost, this was, just to restate the formula, KD divided by Q, and this is $12 multiplied by 3,120 divided by the optimal reorder quantity, 3,870, and this is also $9.675. And of course this is not surprising, because as we have seen in our graphic, these two costs are balanced, or this is in the optimal reorder point, or this is the cost point of these two. So they are the same in the optimal reordering. And now we need to state the total costs. That are from Q, and this is then was D multiplied by C. This is 3,120 multiplied by the 2 cents. This together is 62.4, and then the average inventory holding cost and the average setup costs, which are the same. So I just say 2 times the $9.675, and this means that we have a total holding cost of $81.75.